There's a lot of talk for the right reasons in the industry around the different AI models. But when you think about how do you operationalize those AI models and how do you operationalize an AI workflow in the enterprise, you got to think beyond the model. And there's a lot of other things, other considerations to kind of deal with. And that's going to be really the focus of this talk is going beyond the models and looking at other parts of the stack that needs to be architected in order for enterprise users to scale AI. But without further ado, let's get into this. But I do want to start with the models because there's a lot of stuff happening in the models. So I think it's a great place to start. And the first one is, it is astounding, truly, the speed at which newer models are being made available. Today, if you go to Hugging Face, I just pulled this stat this morning. We're looking at almost 1.9 million models that are available on Hugging Face. When I went to this just a few months ago, this was at like 1.5 million. So you can already see like almost every month you have 100,000 models being added, which is amazing. Now, this is the Hugging Face. It has a combination of open source models and closed source models. So it brings you an assortment of all kinds of models that you can run. But this is not the only kind of repository, or this is not the only database. If you look at NVIDIA and what they have done, they've done a great job of curating a lot of those models, and then they have over 200 models now. And what they have done is really made it easy for consumption. And their approach has been to containerize these models as microservices. They call them NVIDIA Inference Microservices, or NIMs for short. And they have over 200 NIMs that they make available for users to use. And these have been also hardware accelerated. So if you're using the NVIDIA GPUs, and if you run these models packaged as containers, they're already performance optimized to run on the NVIDIA hardware. And the best part is this also works seamlessly in Kubernetes environments. And you can use the Kubernetes scaling mechanisms to scale your models and your infrastructure based on the bandwidth and the scale. All right, so with that said, there are also many ways to consume these models. The models are going to continue to grow, but we kind of see it as like three broad buckets of consumption patterns. The first one, no surprise, vibe coding with the IDEs. This is a direct way and maybe the simplest way to start consuming the AI models directly into your IDE. The second one is public cloud AI. This is where, depending on the public cloud provider you're using, they give you direct access to these foundation models. You can run them in your own kind of virtual private network on these clouds, but they also give you access directly to cloud GPUs. And you can also train your models or bring your trained models to these public cloud environments and consume them. And then the third one, which I believe is where a lot of the growth is also happening, is around private cloud AI. And this is where companies like HP Enterprise, Dell, and Nutanix are taking the lead and providing users with maximum control over their hardware, their privacy, their security, and allowing them to really create these sovereign AI environments. So it just depends where users are along this journey. The point of this slide is there is no one consumption pattern that fits. There are many. And even within an enterprise, you may find one or more patterns that exist. So then the question becomes, with this as the backdrop, how should, let's say, platform teams and how should MLOps teams architect their infrastructure to give agility and speed and give this notion of leverage back to their enterprise users? Now, before we go further down, I want to also share one other key trend and pattern that has emerged. which is really this symbiotic relationship between AI and APIs. We know that any AI endpoint to be consumed, it requires an API interface. It doesn't technically require it, but that's become the dominant pattern and the dominant interface. And then if you have AI endpoints being represented as APIs, you are going to have a real explosion of APIs in the enterprise. And this is where you need to also have an API management framework on top to govern all of those APIs. And then this is why I think we say like no AI without APIs, but also no APIs without API management. And there was a recent article that was kind of published on CIO.com. I put the link here for you guys to see. And it takes this concept even further and argues that as agentic AI takes or has more adoption in the enterprise, the notion of AI endpoints being expressed and being exposed to the API endpoints becomes even more important. So APIs become that core consumption layer for AI, but then APIs also become these secure bridges for the agentic workflows. And that allows you to put the proper governance and use policies in place. And then as APIs are also being used in the context of MCP, they start to give that dynamic endpoints behavior to AI agents. So APIs are the center of this, and this is why I believe that any kind of AI deployments at scale needs to really have strong API management posture to go along with it. So how do you go from here? And what are we seeing from the enterprises that are leading this charter? Well, first they have to kind of decide. It's a sequence of many decisions that they have to go through. And if I were to kind of boil it down to three broad decisions that enterprises have to make, that really guides where they want to take their enterprise AI implementation, it comes down to three questions, right? Number one is the decision for which models to use. Are they going to use only open source models? Are they also going to use or maybe solely use proprietary models? Or is there going to be some hybrid? Or they're going to train their own models and use custom models? I think this is a really important decision, and this will drive decisions further down the workflow. The next decision becomes, where will you run these models, like the deployment decision? Are you going to run them on the public cloud? Are you going to run them on private cloud? Do you have air gap requirements? Or do you have a mix of these requirements? Some workloads absolutely must run in air gap. Some must run on public cloud, whereas maybe the majority of them needs to run in a private cloud, more secured environment. And then the third big decision is, well, how do you build this? Like, how do you procure this solution? Do you have a DIY approach where you take a bunch of different things available, whether it could be in the open source community or it could be from vendors, where you purchase these building blocks and you put them together yourself? Or are you buying turnkey solutions where vendors can just give you everything packaged nicely, where all you have to do is just customize it to your needs? Or is there some kind of a hybrid pattern here? The reality is that these are not going to be binary decisions. And what we are hearing from the customers and the users that we talk to is it is a very heterogeneous environment, a very heterogeneous reality. So they will have a combination of open source and proprietary and custom models. They're going to have deployments that will span the public cloud and private cloud and air-gapped environments. And they also have build requirements where they can get away with DIY, whereas turnkey would make sense in other scenarios. And that is the reality today. So with that being the reality today, what is the approach that we believe in? And this is going to be the central point of today's presentation, is what can platform teams and ML ops teams do to address this reality? And it really comes down to this notion of runtime environments becoming the strategic operational levers. And by runtime environment, we mean there are two very specific runtime environments that we're referring to here. There's the model runtime environment, and then there's the API runtime environment. The goal of the model runtime environment is to really bring availability and resilience to the models itself. That is the single most important goal, is to ensure that your models can run in a available, in a resilient, and in a high performant manner. And it's all about optimizing for inference. Whereas the goal of the API runtime environment is all about API availability and resilience. And this is where you are able to abstract your AI models as APIs and provide the full infrastructure, making it highly available, highly resilient, and highly performant. The struggles that we have seen users run into is when they purchase solutions or cobble together things where you create this embedded characteristic of the API runtime getting embedded into the model runtime, which ends up creating vendor lock-in. And what this ends up happening, there's probably like, three big problems that we have seen, or patterns that we have seen. One is that this embedded notion, it creates incompatibility. So if you have a certain model runtime environment where you're exposing certain models as APIs, that is only going to work with that model runtime environment and with that vendor. It will not be compatible with other vendors. Second is this API runtime environment, when it's embedded into the model runtime environment, it lacks a lot of enterprise-grade capabilities. And the third is that we see a relaxed kind of posture and a relaxed approach towards standards. So, for example, one of the things we've seen very commonly is the OpenAI API standard is not properly adhered to when you try to kind of integrate these two. And a big question, for some of you guys on the call, that you are a customer or you have customers that are deploying this, there's three questions you can ask that will be telltale signs whether you have this embedded offering and whether this creates a lock-in or not. Number one is, does the runtime environment allow you to share your AI endpoints with your developers? The most common way to do this is through a developer portal. Does that have, is that available? That's number one. Number two is, when you're creating these API tokens or API keys to access the model, can you integrate that token generation workflow into your existing IDP? Or does that happen in isolation? And then the third is, when you look at observability, so when you're looking at your metrics, your logs, your traces, the behavior, kind of characteristics of how these models and APIs are working, do you have a vendor? Are you being offered a vendor neutral way to do this, or are they proprietary? Like, one thing would be, is OpenTelemetry something that is supported that allows you to see these logs, metrics, and traces in a vendor neutral way? So you land anywhere of these three questions. If the answer is no, then you know that you're on a path that will create limitations for you as you're scaling. So the way to do this, and the approach that really works well, is to strategically decouple these two runtime environments, but keep them interconnected. And the way to keep them interconnected, and this is where the AI gateway comes in play. Now, I'm showing you Traefik's AI gateway, but it doesn't have to be our AI gateway. The key point here is that you need the AI gateway as a fundamental building block in your architecture that allows you to decouple but still keep the two interconnected so they can share context with each other. And what this allows you to do is to have decoupling of the model governance that the model runtime environment provides, allows you to have the routing governance that the AI gateway provides, and you're able to have the API governance that the API runtime environment provides. It's a very modular approach. It's a very scalable approach. It reduces vendor lock-in and gives the enterprise tremendous freedom, leverage, and the ability to scale and adapt to the changing AI kind of ecosystem. And here's maybe like 5 things, right? The decoupled architecture really unlocks. It will allow you to future-proof your architecture. So models are going to change, right? This is the name of the game. Models are going to continue to evolve and change. Like, do you have the right architecture that gives you the ability to adapt and scale as that's happening? And this is what we mean by future-proof. Number 2 is security. Are you able to centralize and standardize your access control? This decoupled architecture provides that. Third is infrastructure as code. By deploying everything with cloud native principles, with Kubernetes native principles, with infrastructure as code principles, gives you significant leverage in the consistency and the automation of your deployments. And not just infra as code, what this also allows you to do, point number 4, is to deploy and implement policy as code. So as you're deploying policies around semantic caching for efficiency reasons, or you're putting in guardrails for safety reasons, to us, those are policy attributes. And you can deploy policy as code by allowing for this strategic decoupling. And last but not least, we already touched on this, is you also get observability, but it's also, I should say, standards-based observability, where you're able to look at metrics, logs, and traces across your architecture to both monitor and to debug issues. So with this as the foundation, I want to now pass it over to my colleague Emmanuel, who's going to really share with you some common deployment blueprints. And this is going to span both public cloud and private cloud AI deployments, so we can show you how this works in practice for each of them. Emmanuel, please take it away.
Yes, thank you, Sudeep. So you should be seeing now my screen. Okay, so I will show you 4 different blueprints for different use cases. And even in these use cases, we will have different kind of particular scenarios. And let's dive deep. Let's get our hands dirty with the technical things. So the first one is about running AI inferencing in your private infrastructure. Here I'm using Kubernetes as the runtime, but this could be basically anywhere, any cloud provider that has Kubernetes offering, if you have something on premises and so on. I'm using also NVIDIA GPUs, and also NVIDIA provided NIMs, NVIDIA inference microservices, some vetted models to be exposed. And the Traefik Hub will be there as our API gateway. So let's see the blueprint. Here what you can see, what Sudeep explained, are the 2 key pieces. First, you can see on the right here, I hope you can see my cursor pointing, you can see the model runtime environment with the GPUs, with the models in it, and so on. And on the right, you can see the API runtime environment. And then you can also see some users and some personas who will consume the APIs and some additional auxiliary services. So let's walk you through what we have here. First, on the model runtime environment, you basically need some powerful GPUs, or if you run some small models, you are probably fine with CPUs. But I assume here we are talking about enterprise use cases, so maybe it's not even one node here that is connected, but a couple of nodes or even tens of nodes here. You can use horizontal pod autoscaler to scale internally inside the the node itself, or you can use Carpenter or other tools to even scale your nodes depending on your workloads. And you expose these models through the NVIDIA provided NIMS services. And this is where Traefik Hub as the AI gateway, API gateway, and API management solution can tap into in the API runtime environment. And here we can see that there is something on the bottom, OpenTelemetry, which is providing you observability, full stack observability through metrics, traces, and tools, and allow you to see what is going on if you have a distributed architecture throughout your services and so on. You also see some identity providers that will provide our key personas, authentication, authorization, and the identity itself connected through Traefik Hub. And here you can see that we have developers and applications who will consume either your APIs or the web UIs that you provide. And let's start first.
Emmanuel,
Yeah?
we are not able to see your cursor if you are using.
Okay. Then I will just explain on the left, on the right. Somehow it does not show in Chrome. Okay, I'm only sharing the tab. Okay, so first, let's see what the developers will experience. The developers will see an API portal. This is where you publish your AI endpoints that you basically manage as APIs. And also, this is where you can publish all other APIs that you have, like billing services, CRM services, whatever you have. You can publish your OpenAPI specification as a nicely rendered view and attach additional information like custom tutorials, custom ways of workflows, and so on. You can publish your core infrastructure information here. You can also test these APIs, try it out on the fly, and see your subscriptions to these AI endpoints or API endpoints. So this is great for visibility, like discovering the APIs. But what's even more important is that the applications will consume your APIs. So let's see what flow they experience. No matter what are these applications, even as a simple Kirk call or a mobile application or a web application and so on, they will interconnect with the REST API, interact with the REST API. And this is where Traefik provides a chain of middlewares, chain of plugins, let's say chain of policies that you can build up as Lego blocks, starting from what's provided, what's built in, or even making your own custom policies built on Go or WASM-Lang. And this is where you can authenticate, authorize your users, late limit your request, put in security controls, or even since we are talking about mainly AI, the most important thing to provide responsible AI services that you want to guard your content, what is going into the models or what's coming out of the models. You want to block these, you want to mask these, and so on. You want to have semantic caching, and then you also route things, and you want to even experiment with different kinds of models. So this is nice because the chain works in a way that a request comes in on the left, goes through the chain, and then goes out on the right, then also comes back and traverses the chain in the other way around. So you can make processing both on the request and on the response side. So now let's see into these particular bubbles, particular building blocks, how it look like in action. So first, let's see how a NIM service looks like. When you are using NVIDIA NIMs, it basically acts like an operator. It has its own CRD, and you can define which model you want to run. Here on line 8, for example, you can see that I'm using an NVIDIA curated model, Llama 3.1, 8 billion instruct model. And then you have the pull secrets to it on line 11 and 12 that you are able to run this in your environment. You also provide some storage to the model on line starting from line 15, and then you can control the high availability or the replica count, which you can of course auto scale on line 19, and you allocate some GPUs, one or even more, depending on your needs, and then you expose this service inside the Kubernetes cluster. And this is where Traefik will be able to tap into with built-in service discovery, and this is how you can then expose the services. And this is where, for example, let's see the canary, which can use these services. You can see here that the NIM service exposed the Llama 3.18 billion service. And here we can tap into that. And the Traefik service is something Traefik specific. So it acts like a Kubernetes service that provides you, for example, this weight mechanism on line 12 or 16, that you can adjust how much traffic goes into each models. So basically you can achieve like a seamless transition between models without modifying anything client side. You can experiment with different kind of models, totally masked away from clients. You don't break anything. If it's a compatible model, you can try it out. And then this is something that you can leverage then in your routing. So for example, here we see a Traefik native ingress route specification, which defines an incoming ingress route. You know, ingress itself as a specification in Kubernetes world is frozen, almost deprecated, and gateway API will be the next one. But in the meantime, ingress also had some couple of shortcomings, drawbacks, why Traefik introduced an ingress route. I'm just using this one, a Traefik native resource, but this could totally work with the new convention, the gateway API specification. It's just the way how you express your incoming routes. So here you can see Traefik is reaching to from the clients, from your applications. On line 8, on the AI entry point, it's basically a port defined, and Traefik allows you to use these human-friendly names for easy management. And then you write a rule to catch this traffic. Here on line 11, I'm just catching on the host header, but you can build here very powerful expressions with and or logic, match for different kind of headers, match for even the model, match for many things. But here, one driving principle I advise you to do is do not hard code the model into your clients. Try to match the traffic based on generic things like the host or the path, like expose an API with slash API or slash chat or whatever, but do not code the model into your clients, which seems like swimming against the flow, because when you go to Hugging Face and you go to other examples, you always see the model hard-coded into the Python examples, for example. But here, what you want to control is, where you want to put the control is the gateway itself, because models come and go. They will be tested out overnight and replaced to the next day. And then you don't want to publish like a new Play Store application. You don't want to publish a new application version just because you want to consume a better, more efficient, or a better inferencing model. So this is where the AI gateway can add the AI governance. So for example, on line 19, you can see a chat completion middleware added. And basically, this will control which model can be used by the incoming traffic. And then basically, the client request and the gateway provided details will take up the whole request that will be sent to the LLM model. And here we also reference the canary on line 13, that's chat service we provided. And then basically you have the basics of routing laid out. But with this, you still have no control, no policies defined. So let's see what this looks like. So for example, with authentication authorization, you can add the JOT middleware or a JSON web token in longer form. You can use here, for example, I'm using Keycloak to define as the source of truth for this JOT token validation. And here, one thing I also recommend that you should use JOT. wherever it's possible. You can use API key, of course, it's fine. It's worked over the years, but API keys do not have those additional metadata that's incorporated in a JOT. API key is basically just an opaque string, and the JOT embeds some information, some metadata that you can extract in the gateway. For example, on line 11, I extracted the groups information from the JOT token, and I can then reuse this information later in other middlewares. And of course, JOT can have and usually has short-lived expiry date. This means that the JOT token, if leaked, can be only used for 5 minutes. Then you have to use another one because it's expired. So it has many good things that you can leverage. And of course, you can apply API plans to govern the consumption. You can define your rate limits, your quotas, and you can define it even on multiple levels. You can protect your backend as a security measure that your backend cannot provide you, let's say, 10,000 requests per second more, because it will then go down. It will then consume all the CPUs or RAM it has. Or you can define it on the business level. This is what you can see here, like each consumer can access a particular amount of requests per second or per month even. And this is what you can, where you can break way your security protection towards different consumers, so you can hand over these in smaller chunks. And of course, these all will be visible on the developer portal, so your developers will know how much they can consume and how they go over their quota. And then let's see the content guard, which is very interesting to do. You can configure different engines. Here we provide you with a Presidio, but it's basically a plug and play architecture that we can support even more in the future. Presidio comes from Microsoft. Basically, it's Microsoft open source product. It's fine-tuned for personally identifiable information detection, and it can mask or block the information. Here you can see a response rule on line 14 and on that you mask the sensitive information such as an email address or a phone number. So even if you train your model on a sensitive data, you can make sure that the LLM will not return the sensitive data to the consumer. Or you can do the same for the request as well. And you can have even both defined. And you can also not just mask, but also block requests. And with this, you can make sure that you have what's called a responsible AI model, but you want to do cost-effective AI serving as well. Here comes the semantic cache into action. You can use different kind of vectorizers. Here I put Olama as an example, as a local one, but you can use OpenAI here. You can use any provider here. And you can use different kinds of vector databases that will basically act as a store for your prompts and your responses. Under the hood here, what happens is that the model creates a mathematical vector representation of your prompt, and then it will create a semantic search, a vector search based on these, and this is why you need a specific vector database. You can also govern here some aspects of how much distance you allow from different vendors, so how much similarity you allow between two prompts until it made similar or different. And you can control how much history to save from the conversation, or you can even create a read-only cache that you populate with your own curated responses and requests. So basically, you can create, for example, like a frequently asked question database, and then serve it and not allow cache poisoning with storing customer or consumer-generated data. So this is a basic use case I've shown you, but you can go really wide here. And I'm just hinting a couple of additional use cases within this architecture. So when you have day two operations, you want to make it very seamless for even your developers and even your sales team to access these models and cost effectively, and maybe you want them to access the models that were fine-tuned for their use cases, or what you think they should, for example, the developer should use a bigger, larger model because coding requires some specific features that you can only provide through a bigger model, which consumes, of course, more resources, so it's more costly. But you want your sales team or your HR team or other teams who will be just fine with simple answers to consume a smaller model. And you can, of course, do it with Traefik as well. You can route based on these groups that I explained that you can export or surface from the JOT token. On line 20 or 28, you can see that I'm routing based on these groups present as the extracted header from the authentication. And then you can also go wide, like let's say you have a consumption that is treated as a prime hour, for example, like business hours, when you want to use a small, very efficient model to handle a big load. And then you want maybe in the night hours or your off hours, where you want to experiment with something new that you do not fully trust, or you don't know how it will perform, or if it's a larger model, and then you can experiment with that, how it will look like to run in action. And then you can export your observability metrics, your traces, and so on, and see really deep insights of this. And here you can see the similarity. I basically just changed on line 17 that now I'm using OPA, Open Policy Agent, to give me time data. And then I'm using a different rule only based on the time header, and that's it. Everything is same. So with this configuration as code approach, it's really easy to even just copy paste configuration that already exists and build on top of that. And it's really nice to put everything into Git and review it through the standard peer review process, or you can run different kind of analyzers and linters on those code. We also provide these to make sense of your configuration and what will be the impact of the change. So it's not only linting or semantic analysis as well. So these two are just examples that your imagination can really go wide, and then you can really build what you want based on these building blocks. On the next blueprint, we will stay still on the private infrastructure, but now we will be using Kserve. Kserve is a model serving platform, and we will use Hugging Face as the source of the models. As Sudeep explained, there are 1.8 million and even growing models. So we will use, again, NVIDIA GPUs, but now served by Kserve. So you can see the blueprint is very similar to the previous one. There is not much change here. What's changed is basically that there are different models on the model runtime. There is Kserve serving these models, but everything else is basically the same. You can see that the biggest difference is in the inference service, the Kserve specific thing, where you define which model you want from Hugging Face. You provide a token, the authentication towards Hugging Face to download it. You define your CPU requests and memory requests and limits, assign some GPUs, and that's it. Kserve will create a Kubernetes service that Traefik can use similarly as the previous one. So you can see we will tap into the Mistra Medium and Mistra Small service created by Kserve, and then everything else is still the same. The routing does not change too much. You can see basically no character change here, and then all the policies can be applied the same. So you unified, no matter which model serving you use underneath, you have the same day-to operation experience. You abstracted away the model serving layer, the model runtime experience, and now you just have one unified API runtime configuration that you need to maintain. So now we have seen private cloud use cases. Let's see some public cloud ones. First, let's use AWS infrastructure and use AWS Bedrock, which is the managed AI inferencing service. Here you can see what has changed is Traefik Hub running inside the AWS VPC. It can run on AKS, the Kubernetes service or container service, and so on. It runs in connection, it connects to AWS Amazon CloudWatch for monitoring, for collecting the open telemetry metrics, and it uses AWS Cognito as the identity provider. But other than that, what happens is that we will just connect to AWS Bedrock, and to do that, you can leverage something called the AWS Access Gateway, which is a local service that you can run. And if your clients require Open API specification compatibility, then this is basically a translator service that you can put in front of AWS, because Bedrock has a proprietary, their own JSON schema, which is not compatible with OpenAI. And this way, you can abstract away even Bedrock specific things. You just run this service, you run, you put the access key and secret here. You can see it on the bottom, and that's it. Traefik will interact with this gateway, and then the configuration is again unified. We just tap into these exposed local services, and you can experiment with the Canary now on AWS Bedrock provided Claude Anthropic Sonnet models. And then the routing, again, it's the same. Nothing has changed. Your client did not need to change. Now you are even running in a cloud environment, and you haven't need to publish any new version on Play Store. Your clients did not break. Okay, so let's see what has also changed. The middleware for Cognito, and that's the only thing. Now you are getting the user information from Cognito, and that's it. The content guard, semantic cache, and other policies stay the same. And let's see another cloud example with Azure. Azure AI Foundry is an equivalent in another cloud provider, but what will be special here is how we interact with it from Kubernetes environment. Here, Traefik runs in an AKS environment, and it's connected to Azure Monitor for observability and Azure Entra ID for identity provider. And you can see the main difference here is the service definition. We use a Kubernetes native structure called an external name service, which is basically like a DNS, like a pointer towards an outside, a service living outside of the Kubernetes environment. And this is how now Traefik can discover this service in an instant and tap the canary mechanism into again, now we're using different kind of GPTs from OpenAI, but we could be using also Grok, all seamlessly, no need to change on the client. The routing stay the same. I hope you know it now as the back of your hand. And the only change, the biggest change is that now we are using Entra ID as the key validation. So you can see here I think some patterns that are key takeaways. And this is where I give back the mic to Sudeep to walk us through.
Yeah, thank you, Manuel. So let's go to the first point. I think as you have seen, as we have tried to really illustrate this point, that how important and how strategic these runtime environments are. And you must decouple them so you can maintain optionality. And by decoupling the runtime and the model runtime environments, this is where you're going to get this flexibility and this leverage of being able to really enforce the policy at scale and be able to put in these guardrails, have control over the routing, and not have to really force the hard coding of the models down to the application. And this is the third point where we have to operate with this mindset that these models are going to continually change. So you may pick a class, a family of models. So let's say you pick the Sonnet family. Now, that doesn't mean that you're going to stick with 3.7, like 4.0 comes out. You want to continually bake that into your infrastructure so you can incorporate 4.0 and then when 4.1 comes in and so forth. And this notion that one model is going to rule them all, I think that is a myth. And I hope everybody on this call at least kind of sees that, where there is not going to be one model. And the models are continually changing. Like you guys saw the news, Grok 4 came out. Like now they're saying they're blowing everybody else out of the water. So there is no long-term advantage to a particular model. And we don't know, the movie is not over yet. It's constantly changing. So you want to, as an infrastructure team, as an infrastructure person, whether you're on the platform side or on the ML ops side, you want to create an architecture that can integrate this change at any given point. And so I will leave you with the last one is we showed you a bunch of stuff here. Yes, some of this could get pretty complex, although it's very modular. And we would just recommend that you start small. I think the first thing you can do is to implement an AI gateway if you don't already have one in your infrastructure, because that really creates that wedge that gives you that decoupling. And then you can, over time, layer in the API management, which really is the pinnacle. Because if you have both the AI gateway and the API management, this gives you the best opportunity for creating a really scalable enterprise AI architecture. And with that, thank you all.